Hiya, thanks very much. Yeah, it's really nice to speak at such a varied and interesting conference. So what I'm going to talk today about is mostly old stuff from my PhD, which I just finished, supervised by Dan Brown, who you heard from earlier this morning. And it was joint work with Dan. Earl Campbell is now at Potsdam, Joe Warman's at Sydney, and kind of leading toward tentative new work with Ray, who's over there. So basically, like I said, it's old stuff. So in order to make it interesting for me and hopefully for you, I'm going to slice together two somewhat related subjects in the hope that it makes one interesting talk. So I'm just going to throw some stuff at the wall. So the non-locality part, I guess most of you should be familiar with, is that the predictions of quantum mechanics are not compatible with classical intuition. Would anyone prefer which one I stood by?
This one.
This one. Is this the best one? Occasionally I'll do this to make a point, but okay.
If you want to be...
realistic interpretations of quantum mechanics or local variable theories have to be non-local. Take on. They require minimal assumptions, and they found an application, a very nice application in quantum information, mostly in the area of device independence. So, I think you're going to hear about device-independent randomness extraction from Serge later in the week. But it was a case of turning Arthur Eckert's intuition about quantum key distribution using entanglement into something that was actually based on non-locality, instead of just assuming entanglement. And it's been generalised to lots of other cryptographic settings. And also there's a nice connection between non-local games and multi-interactive proof systems. So there's a nice computer science influence there. And like I said, the intuition is that QKD and randomness use entanglement as a resource. You can also violate an inequality without knowledge of the Hilbert space dimension. So why not just directly utilise the violation? So I'm personally quite interested in quantum computing and the role of entanglement in quantum computing. So it's a very old issue, and I suppose one of the great papers in it is to show that there's unbounded entanglement is needed for an exponential speed up in pure state quantum computing. This was a nice result by Joseph and Linden. However, the picture's not so clear. When you go to mixed state quantum computing, things like discord might play a role. So entanglement can be bounded in these situations. But it's generally believed that entanglement is going to have to be a useful resource. So I'd like to focus on particular models which directly utilise entanglement. And so in particular I'll be looking at talking about measurement-based quantum computing. There's another model which entanglement seems to be very prominent, and this is thinking about quantum circuits with unbounded fan-out, which was first talked about by Hoban and Spanner. That should be 2000. Okay, it's 2005. So in the unbounded model, unbounded fan-out model, you have some discrete gate set, and then you're allowed the ability to produce an unbounded amount of ancilli and perform a kind of generalised controlled knot with these ancilli. So you're allowed to kind of distribute some amount of entanglement with these ancilli. And on the other hand, in the measurement-based model, you have some entangled resource, and then you just make single qubit measurements sequentially on your entangled resource. And in a result from a couple of years ago, Dan Brown and Elham, who both spoke this morning on Simon Pertwee, showed that these two models are equivalent, modulo some kind of constraints on the classical side computation in the measurement-based model. And the nice thing was that Hoy and Spellick showed that this unbounded model is extremely powerful. Well, it's not extremely powerful, it's powerful. I don't want to go too mad. So the idea is that time is a commodity, so we want to reduce the kind of depth of our circuits. So why not just use up more space? And then say, well, what can be done in a constant amount of time or constant depth circuits with this unbounded fan-out? And it turns out you can achieve gates such as the parity gate, which can only be done with log electrical circuit. So there's a nice kind of lower bound which says if you want to do a parity gate in constant depth, you need an exponential size gate. Oh, and there's I thought I'd name check, since I'm now at the Oxford group, I thought I'd name check a recent application of category theory to quantum information, which deals with replacing sequential operators with entanglement for mixed state operations. Does that make you happy, Bob? Okay, that's as happy as Bob gets. That's fine. So like I said, measurement-based quantum computing is equivalent to this powerful model of unbounded fan-outs. So the question then becomes, can entanglement be replaced for non-locality, just as we did with device-independent quantum information? Instead of it being based on the kind of mathematical structure, is it based on the raw statistics of what's happening when you're a computer? And I didn't really mention it, but the nice thing about the Bell inequality is that you can obviously violate a Bell inequality by degrees. So even if your state's not quite perfect or your measurements don't quite align, you can still demonstrate non-classicality. So as in the summary, you can utilise this inherent fault tolerance to do, I guess, unwaveringly a fault-tolerant quantum computation. And so the kind of motivation is that we have these powerful non-local correlations, and just to replace kind of sequential operations with these powerful correlations. And a kind of, even if we're not talking about comparing classical to quantum, superficially, can we borrow results from non-locality to make statements about circuit complexity? And so the side issue, this is the kind of other side of the coin of the two things which I'm going to splice together. Understanding non-locality in multi-partite scenarios is a current ongoing major open problem. I mean, even understanding multi-partite entanglement is extremely hard. You don't have much of an insight. And one kind of step up in the ladder is to differentiate between different forms of multi-partite non-locality. So you could just say that you have something which violates local realism amongst them parties, or you can say that they have to violate a certain kind of local realism where parties can actually team up and signal to each other. This was a model first introduced by Svetlitsky. And you can derive the corresponding inequalities for these more general local realistic models. And so the idea is that if we're going to have some sort of distributed information processing protocol, we're going to want something which is kind of inherently n-partite non-local. But whether it's actually useful is, I mean, that's another open question. And as a side note, this kind of ongoing projecting, kind of characterising quantum correlations through information theoretical principles, such as information causality, macroscopic locality and all this. There seems to be very troublesome when you think about multi-partite correlations. There's a very nice recent paper from Tony Yassine's group, which show that in order to characterise quantum correlations, you're going to have to require truly multi-partite principles. And also, you want to differ quantum correlations from more general correlations which don't violate special relativity or non-signalling correlations. But I mean, the way that people characterise this is by considering the convex polytope of these non-signalling correlations, and even for three parties, the space of statistics is horrendous. There's kind of very little intuition about what's going on. So in terms of what insight it gives us about quantum correlations, it's somewhat confusing. Apart from quite a nice recent paper by Tobias Fritz, which shows that there is a kind of a nice duality between Bell inequalities and these non-signalling boxes. And I think Tony is not here, but I think later in the week he's going to talk about a new multi-partite information processing principle called local orthogonality. So this might be a possible solution to some of the problems when thinking about multi-partite correlations. So what am I going to do? Okay. Well, I'm going to attempt to argue that a simple computational paradigm allows some insight into multi-partite correlations, and maybe kind of somewhat ambitiously try and answer what they are as well as what I can do with them. Saying, well, what is their nature and what does this mean for information processing? And my nice simple paradigm is a restricted form of measurement-based quantum computing, where I strip out sequential measurements, and then as soon as you strip out sequential measurements, it overlaps with a really nice, well-studied bell setting. And I'm not going to talk about this, but you can ask me about it later. But this parallel between quantum computing and bell tests is kind of motivated some new modifications of bell tests. You can ask me about that later. So the rough outline, I'm going to talk about a model of measurement-based quantum computing, where measurements are no longer adaptive, and show that it coincides with Baer, Neville, Tchaikovsky, Bruckner, who's just sat there, bell test, and use it to demonstrate the necessity of adaptivity if you want to think about measurement-based quantum computing more generally as an efficient form of quantum computing. And then I'll mention some tentative connections to complexity. And then if I have time, I'll talk about all that second multi-partite correlation stuff that I mentioned and I tacked on at the end. And think about, instead of putting quantum correlations in our computational model, we put these magical boxes in and we just see what happens. Right, okay, I'll start measurement-based quantum computing. It's already been covered by Elham, but it doesn't hurt to go over it again. So the idea is to prepare some multi-partite entangled state, for example a cluster state or a graph state or something from an AKLT state, and then make single site measurements. And then using the measurement data, it informs future measurements and makes corrections for randomness. And all of this is done by some classical side computer, and all the computation results in adaptive measurements. So there's a nice review by Richard Joser there at the bottom. And the thing which is, what it's utilised in this universal blind quantum computation is the fact that there's a nice separation between what we're doing classically and what we're doing quantumly. So we have some resource which we're extracting information from, and then we're using the data extracted from the resource to do some processing. And the experimental challenge, well, mainly lies in the generation of these states, whether they occur naturally or is there some easy way of generating them in the lab. And as well as this kind of nice, clear separation, we have some other insights as well. For example, there is a nice conjecture by Richard Joser which says that within this model we require log depth measurement layers. And also Clifford circuits can be implemented in one time step. And also I think Elham touched upon this, but for cluster states, you only actually require your classical side processing to be limited to XOR gates. So a very limited form of processing. So you can have log depth classical side processing, and so it's interesting that you could recast this conjecture as something saying that you have log depth classical and log depth quantum, and you still got BQP. Okay. So that's kind of a rough overview of measurement-based quantum computing. Does anyone have any questions about that, or was that relatively clear, unclear? Fine. Okay. So the setting of bell tests I want to look at are a nice generalisation of the CHSH inequality for many parties. So we have n parties, 2 settings and 2 outcomes at each site. So there's some bit string, some n-length bit string, describing each choice of measurement, and then some resulting measurement outcome, described by another n-length bit string. And there's a correspondence between the measurements results, which are just plus and minus 1, so we label the bit outcomes, and then we take the expectation value of all these measurement operators, which just is in one-to-one correspondence with just taking the parity of all outputs to be equal to 0, conditioned upon some input. So we've just turned it into a black box situation. We have some inputs, and then we map all these inputs to one single output, just by taking the parity of all outputs. So typically in a bell test you require some shared resource, whether it's shared randomness, local randomness, in terms of classical resources, or some entangled quantum state. And the sites don't communicate to each other, so they're space-like separated typically. And we just have single site measurements and take the XOR of all outcomes. And so if we go back to the Rausendorfer-Riegel formulation of measurement-based quantum computing, we just had the preparation from shared resource, which is typically a cluster state or graph state, where you can imagine some classical spin system. And all the communication is between the classical computer and the resource itself. There's no communication allowed between each measurement site. And then we just process all the measurement outputs and inputs using our XOR computer. So immediately we can see you can map one into the other by getting rid of this adaptive part, pretend it never happened, and then expand on the bell test to say, well, I'm going to allow XOR of my inputs and my measurement outputs as well, and not just my outputs. And we get something which we call non-adaptive measurement-based quantum computing, or nMBQC, if you want to call it for short. So we introduced this model. So essentially we don't have more than one layer of measurements, so we just have one single set of measurements. So you might think, well, what's in this model? Well, we've got Clifford circuits, because I said that you can produce Clifford circuits in one measurement round. But we know by the Gottesman and Keneal theorem that this is classically simulatable. So maybe that's not so interesting. In fact, it's in this parity L complexity class, so you don't even need a full classical computer to simulate these circuits. But look, we do actually have something interesting and something quantum, which is always good. And it's this kind of hilariously titled instantaneous quantum polytime, or commuting Hamiltonians model, where you can just imagine that your unitary that's being performed is just a single unitary, or some one step of a Hamiltonian. And it seems to be the case that there's well, actually I'm not going to discuss this later, so ignore that. It seems to be the case that simulating probability distributions produced by these circuits involves collapsing of the polynomial hierarchy, which is a bad thing apparently. But circuits in this model can be simulated by what are called graph programs, and this is shown in one of the two papers at the bottom. And this coincides with our model. It's not as strong as these X programs model, but it's a nice coincidence there. So you might think, well, okay, well this similarity to a Bell test, since the Bell inequalities motivated so much research in quantum foundations, that there could actually be something deep here. But I mean, I don't want to say that. I'm just more say, well, I'm just going to superficially say there's actually a wealth of literature of Bell tests, which we can exploit. So we perhaps have a new language, new tools, and also a lot's not understood, as I said. So it might be that we can actually offer something to Bell test by looking at this way. It gives us a new vantage point. And instead of these discussions in terms of collapse of the polynomial hierarchy resulting in these IQP circuits, we can replace this conjectured hierarchy with some concrete ideas about what's classical and what's not classical. So yeah, here's the formal kind of setup of what nMBQC involves. So you have some bit string x, which is of length the size of x, and you give it to some classical computer. It produces some data which is linear functions on this input, distributes it to the party in terms of the measurement outputs, the measurement inputs, receives the measurement outputs, and then calculates the parity of all these measurement outputs. And so it's kind of some sort of decision problem where, given some bit string x, you want to produce some Boolean function as the output. And because it's XOR gates, we can represent our measurement settings as linear Boolean functions on x, with P as some sort of binary matrix which describes what functions we're going to distribute to our parties. Where that that little symbol on the left just means matrix multiplication modulo 2. Wrong direction. Okay. So, now we want to calculate correlators the form where the parity is equal to some value 0. By normalization we can choose whatever we want. Conditioned upon some inputs S and this relationship between X and S. So we can just skip out this relation between X and S and just condition the parity to be equal to 0 given our bit string X. When did we start? Did we start at 25 to?
It's been going for 20 minutes.
Oh, okay. Oh, that's fine. So the classical correlations are basically covered by probabilities in a convex polytope. So more generally, we could think of vectors consisting of elements of these probabilities in this R to the 2 to the size of X space. And you can think of these deterministic points as just the Boolean functions. And then we just take the convex combination of all these Boolean functions and we get a convex polytope. So this is, each extreme point just corresponds to some deterministic Boolean map, and then we just take probabilistic combinations of them. And so for classical resources, we also have a convex polytope. And that's if we consider the deterministic functions reduced by local and variable theories. So we just do this by saying that the parties have access to some shared randomness captured by lambda, but because of local realism, if they wanted to do something deterministic, it could be only influenced by lambda and their measurement input. So you just get this simple bit-to-bit map here. Take the parity of all the bit-to-bit maps, and you just end up with a linear Boolean function. And then we just use the definition earlier from our measurement inputs, S related to X. And so the local invariable polytope is just the convex combination of linear Boolean functions. Okay. So all we did really is rederive this Bernoulli-Zukowski-Brooklyn, sorry I cut you off just there, polytope. But now we have pre-processing on data, so we're allowing the ability to perform these arbitrary linear functions on the inputs. And the nice thing about this is that these linear functions are just linear functions on X, so it's independent in terms of how many parties we have. So there's now the dependence on S has just been completely removed. So you could just imagine increasing the number of parties and the polytope will just be the same. So we just use the same properties of the polytope defined by the size of X. And if you want a Bell inequality, then you want something which is down here. But anyway, it's just a facet of this local invariable polytope. Okay. And if we want to look at quantum correlations, then there's a nice result which basically says that the extreme points of the quantum region are defined by measurements on a GAZ state. And so you optimise over these angles here, and you can just basically define all the region. And so if you optimise your angles in such a way, then you reach the maximum distance away from one of these facets, and you maximise your violation. So if we increase X for the classical region, well, all we do is just stay within these linear Boolean functions on X. But for the quantum case, because we're allowed this angular dependence, and we replace values of S with these functions on X, by increasing n, we can actually saturate the whole of the computational region. So for a given nonlinear function f of x, we can achieve these points here. And that's purely just because using the relation between linear functions as being linear independent over the real line. And because they're linear independent and they're in this cos function, all linear functions define some linear independent basis, and we can use this basis to achieve any function. So this exponential requirement for the number of parties is actually tight for some functions. So for this one, which is the n-partite AND function, we actually require the number of parties to be exponential in the number of inputs. However, there are some functions that actually only require a linear number of parties. But basically, the short end of this is that we can't actually efficiently perform circuits in NC to the 1, which is mixed class, which is just log depth polynomial size circuits. So this function here can be performed easily with a log depth polynomial size circuit, but we can't even do that in our restricted model. And since it's in P, and we know that BQP, P is contained in BQP, we need additivity. So it's a nice simple complexity argument. And there are nice analogues between the two models as well. So, as shown by Werner and Wolf, and restated by us in 2011, 10 years later, quick off the mark, the universal resource is the GAZ state. As we've shown, that the extreme points of this quantum region is defined by the GAZ state. And there was a nice result which I only discovered the other day, which is by Itamar Petrovsky, which showed that if you wanted to violate an inequality substantially, then most states are not actually good for this. So we know that GAZ states and certain measurements on GAZ states give us an exponential separation between quantum and classical. This is the GAZ-Mermin argument. But if we were to choose a state at random, I mean the chances are it will be entangled, and we chose our measurements, you would only actually get at most square root over n separation between the two upper bounds. And so they're kind of nice analogous results in full measurement-based quantum computing. So there's a myriad number of universal resources, including the cluster state and graph states. And there are two concurrent results which showed that if we were to pick some resource at random, it would be highly entangled, but it won't actually be very useful. So yeah, to recap, in terms of computing, we've demonstrated that adaptivity is really a useful ingredient for the Rausendorf and Briegel model. And you can use it just by considering tools from the literature, impedance qualities. And what's quite nice is that the road goes both ways, and that our result seems to influence a nice result in circuit complexity back in this quantum circuits with unbounded fan-out model. So using our result, you're actually able to show that there are some equivalencies between complexity classes. So if you don't even care about a gap between quantum and classical, then you can actually show something non-trivial in terms of quantum circuit complexity, which is actually quite nice. And also, as an aside, you can relate some of these models to what are called XOR games, which is a very obvious translation. But the thing that I guess is not quite satisfactory in terms of non-locality is that in order to saturate the whole space, we required an exponential number of parties. Yet we know that there exist imaginary resources called Pescu-Rorley boxes. We just woke up when I said Pescu. That do this efficiently without allowing signaling. If these imaginary objects exist, then we have lots of computational power, because as I've shown in a set, we can actually encode Boolean functions in them. But what's also interesting is that, as I mentioned earlier, this kind of n-partite non-locality issue. And even if you just have some kind of bar-partite non-locality, you can still violate these inequalities, because you're still guaranteed to be outside of this polytope. But you can still actually, if I get time, you can still extract useful information about looking at these truly n-partite non-local boxes. So in the last part, which I think I have 5 minutes for, I want to just quickly say how we can utilise these imaginary resources, these PR boxes, as a way of understanding kind of multi-partite non-locality. So a PR box is a device which does not allow communication, is not realisable in quantum physics, but actually does do something. It violates the CHSH inequality with the maximum algebraic value. And also, if you had an unbounded amount of them distributed between two parties, you can trivialise any communication complexity task performing a Boolean function. And so you can just make a natural generalisation of saying there's n parties and the systems are only restricted by the inability to signal. So the statistics on a subset of the parties must be independent of the full bit string. And kind of a natural generalisation of the PR box is this thing at the bottom, which is called a full correlation box in this paper by John Barrow and Stefano Paragno. And you can see just basically these things locally are completely random because they're just it's just a random outcome, but the thing as a whole is correlated and produces some Boolean function. And these boxes, interestingly, can be simulated by bipartite resources. So in a kind of a nice analogue to our measurement-based model where we just required kind of bipartite entanglement gates. And this is just by just considering the Boolean complexity. The PR boxes produce an AND gate for you, and you can just decompose any Boolean circuit into ANDs and XORs, and you're away. But another interesting aspect is that you can't simulate all boxes which satisfy non-signaling with PR boxes, even an unbounded amount of PR boxes and shared randomness. I mean, you can't even simulate some non-local quantum correlations. That's actually quite interesting. It's an interesting point. So some of these boxes, for example, can be useful for this non-local game called Guess Your Neighbour's Input. Guess Your Neighbour's Input. But I can't think of any other examples where some of these weird boxes will be useful. But we showed in this paper that if these functions take a particular form, where you can't actually decompose the function into some sort of disjoint sum of functions on smaller boxes, then you actually single out particular vertices of the non-signaling polytype for many parties. And this generalises to a larger number of measurement settings and outputs of each side. And these boxes also coincide with things which are what are called truly n-party non-local boxes. So I don't really get to discuss it, but the point of what I was trying to say was really that I guess concepts are often best understood when put to use. And I think this non-adaptive measurement-based model provides a very nice natural framework to look at if we plugged these boxes in, then what kind of computational power do we have, and whether this can be mapped to some sort of circuit complexity model. And the thing that's quite nice is we just can prove some things just by looking at the functions instead of probabilities themselves, and instead of having to consider this whole horrible convex polytope. And we can think about these things which are weird resources which don't have this full correlation box type, and just ask the question of, well, what are they useful for? But I think Samson's going to talk about the nice connection between, you're going to talk about the logical band inequality stuff. So I think there's going to be some nice overlap there. But the point is, I was trying to get at, was kind of the Boolean circuit approach is perhaps kind of more intuitive in thinking about convex polytopes, and you get a lot for assuming quite little. Yeah. Yeah, so to summarise, by starting with an extremely simple framework, it's nice to extract new connections and results, whether it's between ideas of non-locality or circuit complexity, or determining these fanciful objects called non-local boxes. And some work which has been done with Dan Brown was actually just to think about how to reintroduce adaptivity back into the model. And so one attempt which was quite successful was to actually consider post-selection. And if you're interested, you can read that paper. But you can actually probably imagine more interesting models of saying, let's allow some amount of communication between measurement rounds, but we could probably still utilise quantum resources to do something interesting. Okay, I think I'll leave it there and just leave the open questions up there. Okay?
Yep. Questions?
Do you know the answer of any of these questions?
Do I know the answers to any of these questions?
Or
Yes.
have any comments on that?
Yes, I know all of them. But I don't have time to go through.
Can I ask the first one?
Yes, why not? Do you want yes or no answers?
No, what item you meant to link this parallel complexity to
Yeah, so
entanglement?
Yeah, yeah. So, I mean, the parallelising power has been linked to entanglement, whether you could actually go on further and say that kind of parallelisation within some sort of non-local
It's
resource.
kind of the version of the Joseon no resulted in order to get the parallel power.
Yeah.
Well, we still don't know even there is an extra
Well, that's
parallel.
my second. Yeah, yeah, yeah.
It's
Yeah.
about.
Yeah. So, I mean, obviously the thing is, with the non-locality, there's actually a concrete concept as opposed to some kind of mathematical construction. So that's the thing where you can actually say, well, look at the statistics. What are the statistics giving you? Whether it can prove you anything efficient, because I mean, obviously the statistics by their nature aren't efficient, but you can imagine certain situations where, you know, the structure would give you something.
Any other question? I mean, I have one which is on relevance of delta inequalities for computation and computation classes. I mean, usually people do what you have done, actually use these inequalities and then adapt measurement-based computation in the sense that it's non-adaptive measurements.
Yeah.
But now, even if you in the bell setting allow adaptive measurement, this will require just few bits, you know, just to give you.
But like the GXZ, I mean, requires 1 bits or something like that, yeah.
And nevertheless, it seems that measurement-based, I mean, we know that measurement-based quantum computation is universal quantum computation, so they are, you know, they are exponentially better than classical computation. And in measurement-based computation, we believe that this advantage comes at the end of the day, just through the communication between the measurement sites. So what I want to propose that the other way around, starting from the known quantum algorithms with the measurement-based computation, can tell you something about what are really efficient bells and inequalities. Even if you, in a sense, that even if you lack a little bit of communication, you save a lot of.
No.
Yeah.
I think this is one approach.
Result?
No, not. It sounds like a brilliant idea, I'm going to nick that.